Hi everyone, and welcome back to Astronomy Fun Facts from an Astrophysics PhD student. Today, we are going to talk about how we find exoplanets, because this is a big deal right now in astronomy. Everybody is looking for planets outside of our solar system. Now, there are several different ways that we detect exoplanets, but today I'm just going to talk about the main one, which is called the transit method. A key thing to note about any of the methods for detecting exoplanets is that when we say we detect an exoplanet, that doesn't mean we actually see it with a telescope. Our primary ways for finding exoplanets is to look at the light from the star that they are orbiting, because that is so much easier to see than some small rocky body. Okay, so here's the transit method. What you do is you look at the light you get from a star, how bright it is, over time. And you'll notice that if something passes in front of the star, like say a planet, that light decreases. You get less light because some of it is being blocked by the planet. We call these plots of brightness against time light curves, and a lot of people right now are just looking at the light that comes from stars trying to detect these curves. The issue here is that real data is messy. If you look in this plot above, ignoring the red line, it would be pretty difficult for you to notice that there was a dip in there at all. So this is one of the big challenges that exoplanet scientists face, is actually distinguishing when there is a drop in the brightness. But if you can actually find one of these light curves, it can tell you a lot about an exoplanet. The depth of these drops tells you about how big the planet is, because the bigger the planet is, the more light it's going to block, and so the larger the decrease in light from the star is going to be. The longer the time it takes for this light curve to happen tells you about the orbital radius of the planet. Planets that are further away from their star are going to move at slower velocities, so they're going to spend more time crossing in front of the star. Now, we found almost 4,000 planets using this method. It's really powerful and really useful. And from it, we can learn things about a planet like its size, its orbital radius, and even the composition of its atmosphere, which then allows us to detect the ingredients that we think are necessary for life. Hi everyone, and welcome back to Astronomy Fun Facts. Today, we are going to talk about our favorite red planet. Specifically, I want to talk about the geology of Mars, because there's actually some really interesting things going on that planet. To start, did you know that Mars has the largest volcano in the solar system? It's called Olympus Mons, and it is freaking giant. It is over 16 miles high, which is 3 times taller than Mount Everest. But if you were standing on it, you wouldn't even be able to tell that you were on a mountain, and that's because it's so wide. It's about as big as the state of Arizona, or here it is overlaid over the entire country of France. So even though it's so tall, it's got such a flat slope, you wouldn't really be able to notice if you were on it. Now, Mars also has Earth beat in terms of depth as well as height. Mars has its own version of the Grand Canyon, called Valles Marineris, or Mariner's Valley. It goes around almost 20% of the whole planet. You can see it here. It's this giant gash that's about the size of the continental United States. That makes it 2,500 miles long. The Grand Canyon is only 500. And compared to the Grand Canyon, which can get up to 1 mile deep, this baby can get 5 miles deep. Mars really wanted to outdo us in terms of geology. Something that's important to note is that unlike the Grand Canyon, which was formed by the Colorado River cutting through it, this was not actually formed by water. We think that this is just essentially a giant tectonic crack in the surface that, excuse me, cat? Floop. That formed as the planet was cooling. Okay, so I'm walking home from my office, and it is a gorgeous blue sky Arizona March day. And I thought I would do a little astronomy fun facts. And today's fun fact is around the age-old question, why is the sky blue? So our atmosphere is made up of a bunch of different gas molecules, and those molecules have a finite size. When the light from our sun reaches the atmosphere, that light comes in a bunch of different wavelengths. As it turns out, the shorter the wavelength of light, the more likely it is it's going to hit some of those gas molecules. When this happens, we call it scattering. Now, what color light has the shortest wavelength? Blue. So, while most of the light from the sun will just come straight through the atmosphere, and so we see those yellows and whites and reds, the blue light will get scattered by all the different molecules, and so it looks to us like the blue is coming from everywhere, whereas all the other colors come from that local source of the sun. As it turns out, this scattering of blue light is actually something that we see in extraterrestrial space as well. There's a lot of dust in the galaxy, and in dusty regions, the blue light from stars is going to get scattered more than the red light. So when we look at starlight coming from regions of space where there's a lot of dust, the stars actually look more red than they are in actuality because the blue light is getting scattered by the dust that the light has to travel through, just like the blue light gets scattered in our atmosphere. Hi everyone, and welcome back to Astronomy Fun Facts from an Astrophysics PhD student. Today, we're going to do a Speed Around Fun Facts Solar System edition. First up, did you know that Uranus, our favorite inappropriately named planet, spins on its side? Every other planet in the solar system orbits roughly perpendicular to the plane that they go around the sun. But Uranus is tilted 90 degrees. What's up with that? We think collisions, and you'll find out that this is an answer to most mysteries in the solar system. Maybe something hit it at some point in the past, and that's why it behaves weirdly. It's the astronomer's favorite go-to explanation. Next up, we have the crazy fact that the magnetic field of the sun looks like this, and we don't really know why. It's absolutely bonkers what's happening with the magnetic field lines on the sun, and the full modeling of the plasma in the sun's outer levels isn't really complete. And finally, did you know that we don't even know where the solar system ends? In fact, there is a theorized region of space called the Oort cloud, which contains hundreds of thousands of tiny little rocky and icy bodies that orbit the sun many, many times further out than anything we've seen before. We think that this region of space is the home of the comets that we see that have really, really long orbits, but we've actually never been able to find it. So maybe this is the edge of our solar system, and maybe not. We don't really know. Now, I can make a whole series just on what we don't know about our solar system. The list is huge, and you can imagine that the solar system is the one part of space we can actually get to now. So imagine the mysteries that exist outside our own solar system. Astronomy is wild. Hi everyone, and welcome back to Astronomy Fun Facts from an Astrophysics PhD student. Today, we are going to talk about light, and more specifically, how light is used in astronomy. Now, we classify light according to the electromagnetic spectrum, which essentially takes light and breaks it up into different categories based on the wavelength. We're most familiar with visible light, which is light that has wavelengths from about 400 to roughly 700 nanometers. But this is only a tiny fraction of all of the different forms that light comes in. The wavelengths of light can range from 1/100,000th of a nanometer all the way up to more than 100 meters. And so the electromagnetic spectrum breaks these into categories like gamma rays, X-rays, radio waves, microwaves, and astronomers are interested in every single one of these wavelengths of light. As it turns out, different objects in the universe will interact with light and produce light at varying wavelengths. So if you were to look at one object in visible light, it might look completely different than if you were to look at it in, say, the infrared range of wavelengths. There's a lot of great examples of this, like this image that shows the Andromeda Galaxy in a bunch of different wavelengths of light. We are most familiar with this image here in the visible, but as you can see, if you were to look at it in the X-ray, it would look completely different. Same with these images of the Crab Nebula. Now, what causes these images to be so different in different wavelengths? It's simply because our universe is made up of so many different things, and all of those things will interact with light in a different way. Something like dust will emit at really long wavelengths in the infrared, whereas a very high energy event like a supernova will produce a lot of very high energy waves like gamma rays and X-rays. So astronomers pick and choose the different wavelengths of light they want to observe based off of the phenomena or objects they want to look at. This is why there are so many different types of telescopes, and astronomers are always clamoring for more. Different telescopes are designed to look at different sections of that electromagnetic spectrum, and you can't use a radio telescope to look at light in visible wavelengths. It just doesn't work.